If you think about how to define the degree of a polynomial in multiple dimensions, you will realize that's not that simple. There are many definitions that are possible, and that's what we're discussing in this video, namely the total degree of a polynomial versus the maximum degree of a polynomial, and what this means for quadrature. So we know that if you think about tensorized grid quadratures, tensorized grid quadrature rules integrate polynomials up to a certain maximum degree exactly. What this means, so the tensorized trapezoidal rule for example, integrates this one here, p of x and y, was a plus bx plus cy plus dx times y exactly. Why? Because it's based on integrating such polynomials in every cell exactly. And now the question is if this is a polynomial of degree 1 or of degree 2, because the question is how do you view this term here, x times y. And in the notion of a maximum degree, I would call this a polynomial of degree 1 because the x and the y appear with an exponent of 1. So this polynomial has maximum degree 1. And I will write this as max degree from now on. 1. And now, well, what the main idea of sparse grids is, the way I present them here, is that they integrate polynomials of a certain degree exactly. So sparse grids, or sparse grid quadratures, I should say, on the other hand, integrate polynomials of a certain total degree exactly. Yeah, so this polynomial here would have total degree 2 because it's 1 in x, 1 in y, and I'm adding them up, so that's 2. And you can see that if I now ask for the polynomials of max degree of a certain order and total degree of a certain order, you will see that with the total degree you have less unknowns. Yeah, so only this part would have total degree 1, and this already would be total degree 2. So the sense of total degree, and if I have a quadrature rule that uses a minimum number of points to integrate those polynomials exactly, I can hope for less nodes than a tensorized grid. So that's the main idea. And just to make things clear, let's look at the table of max degree polynomials and the corresponding monomials. And let's do the same thing for the total degree. And here are the monomials that have this. So here we have 0, 1, 2, 3, 0, 1, 2, 3. And the max degree of order 0 is only the monomial 1. That's the same for the total degree. Now max degree 1, as I've said, in this polynomial here, all these three terms have max degree 1, and those are all in 2D, whereas total degree is only x and y. And then with the max degree, we have those polynomials of order 2, x squared y, x squared y squared, xy squared, and y squared. So it's 5 of them. And in total degree 2, we only have x squared, xy, and y squared. Yeah, because again, this would be considered total degree 2. This would even be considered total degree 4. And you see where this is going, but let's write the final lines. So this is x cubed y, x cubed y squared, x cubed y cube, x squared y cube, xy cube, and y cube. And it's far less here, so it's only x cubed, x squared y, xy squared, and y cube. Yeah, so you see that those are two different notions of what the degree of a polynomial is. Both are legitimate. You see that in one version of it, the total degree, I'm much more conservative about what it means to call a polynomial of a high degree polynomial. Yeah, because or on the other hand, in max degree, it's far more polynomials that I say are of a certain degree.